Now we are in a new building, so we are yeah. Okay, so
do you want to say anything about this picture?
Yeah, just leave it there for a while. It's Halloween, so people are working in costumes today.
Yeah, I think it's Chen.
I just took this picture for the people who are not here to see that you can still do more math even though you can wear Halloween costumes.
Oh.
Chen, it's a joke. It's a joke.
So definitely this is the new building, right?
Yeah, a new building next to the old one, because there's engineering took over and now they built a new one for us. So we are on the third floor of a new building.
I see.
And it has blackboards everywhere. You can see in the back of my office, it's all the wall is blackboard.
Oh, that's great.
And the corridors are blackboards and everything.
Right. It's very convenient to do the brainstorm.
Yeah, exactly. So we'll wait a couple of minutes for people to log in. There's a lot of entropy in the group today because of the Halloween. So
Is this similar also open to some audience outside of Brown?
yeah, actually, you will see you have people from around the world. We have people from Brazil, from Turkey, from China, from Lehigh University, I see now.
I see.
From
I see
Johns Hopkins
here.
University, from University of Georgia. Yeah, many people.
I see.
Heli. Hi.
Yep.
Can you see? People are dressed up today for the so they do math. Today is the day where you do math with dressed up.
Wow, yeah, I see that. That's Adar, right?
Yeah, but other members also are dressed up, like queens and kings and Sultan Ahmad, maybe Ahmad. Ahmad, can we see your costume?
Adar, you look great.
Ahmad, can we see your costume?
Wow.
There, you see, he's a sultan.
It's like a princess from.
No, he's a sultan. Cool. He's a sultan, and you can see. Yeah. And nice. Here we have Kasia. Tell us what you are dressed up like. Kasia, what are you dressed like? Are you a queen? What are you?
The princess? Oh, elf. Okay, yeah, I can see that. Yeah. I heard that the cashier is actually taking my seat, right?
Yes. You have the same height.
Oh, whoa, really? Okay.
Are you dressed up today for to go to school?
No, unfortunately, no.
Dr. Yu is always dressed up. I know.
No, but I mean Halloween.
Halloween.
Dress up as a nerd, yes.
And some data went to find a red nose so she can our hostess, but I don't know if she's back yet. A couple more minutes and then Zogran, are you the host today?
Yeah, let's start. I see 29, 30 people here.
Okay. Yeah, we can start. Yeah.
Let me make sure we're recording. Oh yeah, we're recording. Hello everyone, welcome to this week's Queroz seminar. We have two talks today. The first talk is given by Zhang from University of California, Santa Barbara. Professor Zhang is an assistant professor of electrical and computer engineering. He received his PhD from MIT in 2015. His research focuses on uncertainty quantification and tensor computation for semiconductor chip design automation and responsible AI system. Without further ado, welcome, Professor, and you may want to start the presentation.
Sure. Can you enable me to share the screen?
Give me a minute. Oh, I make it. Okay, I already made you the co-host.
Okay. So can you see my slides?
Yes.
Okay. Hello, everyone. Thanks for George's invitation. And it's very nice to come back to give a talk, although it's remotely. And actually, I had a very nice experience of visiting George's group in 2013. And that year, I learned a lot about high-dimensional uncertainty quantification. And actually, that experience actually was very, very useful and very helpful for my career development. And today, I will talk about some of the work about the responsible AI in my group. Especially, I will talk about how to handle the responsible AI in the inference and in the training process. And this work is actually is done with my student called Hawkins, who is now at Amazon, and my current PhD student, Chen. And we also have some collaboration with Professor Chen Xiaoli with the math department from the National University of Singapore. And we know that because this AI wave, actually right now, deep learning is almost using every aspect of our daily life, right? Such as medical images, speech recognition, VR. And recently, because of a lot of our work in the mathematics community, especially by the pioneering work in Joyce's group, physics info neural network has also been used in scientific computing. And under this AI wave, we have seen that AI has surpassed humans' capability in many application domains. It's not surprising to see that AI has surpassed human in the image recognition, and also in the and also in the Go game. But actually, what's more surprising is that recently, in the DeepMind, they have shown that using the deep reinforcement learning, they can find better matrix multiplication algorithms than the state-of-the-art technique. And we are very happy about the prediction performance of AI, but actually accuracy is not enough. And actually there are more and more needs about the responsible AI. So what is responsible AI? There are many definitions. And among the many definitions, I like the following one. It's very simple, but it's very clear. So it says that we should design and deploy AI with good intentions and with positive impact, both technically and societally. So good intentions mean that we should use AI in the good applications to benefit human beings and to benefit our society. Positive impact means that, okay, it should, for instance, help the technical development or help the society development in the good way. Here are some examples. If you look at the AI development workflow, actually there are many requirements from the responsible AI perspective. For instance, if you look at the data collection process, normally we require the data collection process to protect the privacy of the users, right? We also want to make sure that the data collected is not biased. And then in the training process, nowadays actually normally the big companies use a lot of hardware resources to train the deep neural networks. That actually causes a lot of the environmental issue, right? And the training is also very, very expensive. It's not affordable for many of the small research groups and for small companies. And in the inference stage, we hope that the AI model can be trusted, right? There are some requirements about the fairness, about the robustness, and also about the explainability and the interpretability, right? And in the application level, if we want to make sure that AI is actually is applied to some good application domains and to benefit our society. Here are some examples, right? Like for instance, we can use AI to improve the biodiversity, right? We can use AI to combat to fight against climate change or to prevent the pandemic. But today in my talk, actually, I will focus on the two-stage inference and the training. So in the inference, in the first part, I will talk about how to actually enhance the trustworthiness of AI using a self-healing technique. So when we talk about the trustworthiness of the deep neural network, actually this is a very big topic, and there are many requirements toward trustworthy AI. For instance, if you look at the model, we may want the model to be interpretable, to be explainable, right? And if you look at the performance on the attack preparation, we want the model to be robust, right? If you look at the social impact, especially if we deploy the AI in education, in animation, and in finance, we want the model to be fair. So my talk actually is especially about the robustness. So especially how we can use the self-healing to improve the robustness of the deep neural network. So what is the robustness issue? So we know that deep neural network can have very high predictive accuracy if it's trained well and if it has expressive power, enough expressive power. But one of the problems is that the AI model often is very sensitive to the very small perturbation or attack. So here is the example. If you use AI in the autonomous driving, for instance, to recognize the traffic signs. So on the left, we have stop sign, right? But if you perturb the stop sign a little bit, for instance, by a few pixels, or maybe the image is blurred by some noise because the camera issue, right? And then very often the deep neural network can make a wrong prediction. For instance, it may recognize the stop sign as a sign of right turn. So in this case, the autonomous vehicle may make a wrong decision, and then there could be a traffic accident. So to address this issue in the deep neural network community, actually, the mainstream strategy is to think about this problem from the attack and defense perspective. Many groups have developed a different type of attack algorithms to fool the deep learning system, and correspondingly, many other groups, they have developed a lot of defense algorithms to protect the deep networks. So definitely there are many impressive results in the deep learning communities. But my argument is that this is actually an endless game, right? For instance, given a deep network, we can always design many types of attacks, right? And then for that attack, of course, you can design a defense algorithm, but other groups they can propose another attack algorithm to destroy the whole system. And also the bigger challenge is that in the practice, actually, even in the practice, we don't know what type of attack information we will have in advance, right? So for instance, and also in many cases, actually the robustness issue is not caused by the attack. For instance, if you just look at the autonomous driving system, and the autonomous vehicle make a wrong prediction, it's not because someone attacked the vehicle. Normally, it's because that the camera, for instance, the camera accuracy is not good, or because the weather condition, right? For instance, because of the fog, right? And then the camera, the image captured by the camera actually becomes very blurred. So I think that, so I believe that we need to rethink this attack and defense strategy. So one strategy that I'm thinking about is actually the self-healing mechanisms. So what is self-healing? So self-healing actually widely exists in the nature and in biology, and it has also been used in some engineering domains. So self-healing is hard to find a rigorous definition for self-healing, but I like this description. It says that the self-healing is actually the ability of system progress that by nature or design tend to correct any disturbance brought into the system. Here I'd like to give two examples. The first example is the self-healing in the neural system. Because of some damage to the neural system, we know that the connection between the nerves, right? It may be disconnected. And one mechanism in the neural system is a regeneration process. So actually, some new axons could be generated to repair this issue. And another example of the self-healing is actually the immune system in our human body. For instance, during the COVID-19 pandemic, actually a lot of people they got the virus, but actually a lot of them actually they feel okay. So why? That's it, because of the immune system, right? We got the virus, but the immune system actually automatically handle this issue and to protect us from the virus. So if you look at the immune system of the human body, actually it's a feedback control, right? So when our body is affected by the virus, actually we may there could be some symptoms inside our human body. We may feel it or we may not feel it. But after the slight symptom appear, actually our immune system cell actually will get the feedback, and then it will trigger, for instance, the T cell and Y cell to kill a lot of the kill the virus or the bacteria. That's why actually our human body actually keep healthy, even we are surrounded by so much virus and bacteria. So from these two examples, we can see that actually there could be many possible ways to implement the self-healing. And my background is actually, my original background actually was from the design automation for semiconductor chip design. So I'm very familiar with this feedback control process. This self-healing idea actually had already been implemented in the integrated circuit design. So in the integrated circuit design, the integrated circuit chips are fabricated in the nanometer scale. So when we do the fabrication in the nanometer scale, actually it is very difficult to control the process variation, to control the very tiny geometry or the material property. So as a result, after the fabrication, the chip performance actually might be different from our design on the computer. So some chips will work very well and some chips will not work very well. And what's terrible is that in the practical fabrication, normally we don't have exact description about the process variation. So we don't know which part will fail and which part will not fail. So sometimes it's very hard to do the prediction and to do the optimization in advance. So a very effective way to address this process variation issue is actually to use the self-healing in the chip design. For instance, on the left figure, we show that in the black box, we have the original circuit, right? This original circuit could be, for instance, a clock circuit or could be an oscillator. And under the process variation, the circuit may not work very well. It may even entirely fail to work. But instead, to directly fabricate the circuit, we can place some sensors on the chip to monitor some key performance, such as power consumption or frequency or phase of the circuit, right? And based on the measurement, we can detect if the circuit is working in the normal state or not. If we find that the circuit is not working in an abnormal state, and then we can do a control, right, to tune some circuit parameter, such as the bias voltage, right, or such as the capacitance value, to change the circuit performance to make sure that it can work well again. So on the right, this is actually a typical example. This is a realistic radio frequency system on a chip design and developed by UCLA 10 years ago. So this is the story actually of the self-healing in biology and in the semiconductor chip design. So the question is, can we actually apply this?
Zheng, sorry,
Yes.
can you say something about the chip, because I cannot? It's a small thing. So what's the special about it? What is the feedback mechanism here?
Oh, I see. So normally, for instance, if you do the chip design, for instance, if you want to design a CPU or design a clock circuit, we just design the circuit, right? So it's in this black box. This is the original circuit. So normally we design the circuit and then we fabricate it, that's all. But the transistor, for instance, because of the tiny geometric variation or material property variation, so actually the original circuit performance may not perform as we predicted, right? For instance, we want the circuit to have a frequency of 10 gigahertz, but actually it might be, in practice, might be 9 gigahertz. It might be slower than we expected, right? So how can we do that? Actually, instead of just directly fabricate the circuit, besides the original circuit, we can also add some sensory circuits and also add some control circuit blocks. For instance, we can measure some injection current, or we can measure some phase signal, or measure some.
I understand the diagnostics. What's the control for this particular case? What is the feedback control?
The feedback control could be, for instance, we can design some control algorithm and then to control, for instance, the bias voltage or some capacitance value inside the circuit.
Okay, so this is like one parameter. You try 2 parameters.
Yes, but in practice, we also. It depends on the system. If we have small circuit, maybe we only need to control a small number of key parameters. If you have very large system, we may need to control more parameters, right?
Okay.
Yeah. So the question is, can we apply this kind of self-healing technique to deep learning? So actually, if you look at the biological system, and if you look at the circuit, they may look very different from the deep learning system. But actually, if we think about them from the mathematical way, actually there are some connections. If you look at some deep neural networks, such as the residual neural network, recurrent neural network, and the normalizing flow, we know that if you do some continuation of the model, and then they could be described by the ordinary differential equation. So in other words, if you do, for instance, numerical discretization, such as the forward Euler, and then we can get the deep network, right? And on the other side, it is very well known that for the electronic circuits, no matter it's a linear circuit or non-linear circuit, based on the physics, such as the Kirchhoff current law and the Kirchhoff voltage law, we can also describe this circuit as ordinary differential equation. That's exactly the mathematical foundation of some electronic design automation tool. They describe the circuit as a large-scale ordinary differential equation, and then they use the numerical solver to do the simulation and optimization. So actually, based on this concept, based on this connection, actually, it's possible actually to apply the self-healing concept in the biological system and in the circuit design to deep neural network. So here I like to show the key idea. So here, if you just look at the feed-forward propagation with deep neural network, right? We have the input data, and the input data will propagate forward through every layer. So this is just a feed-forward structure of the deep neural network, and it's finally in the last layer we have the label. But if you look at this deep network from the dynamic system perspective, and then every layer is just like a snapshot of the state vector at every time point, right? So now, assume that in the deep network, the input data might be perturbed, it might be attacked. So here we said, okay, it might be, because in practice we don't know if there exists attack or perturbation or not. Okay. So we don't know if the system is affected by the perturbation or attack or not. But what we can do is actually inside every layer we can add a monitor. So here we use a monitor. We use a E0 as a monitor to monitor the feature vector in every layer. And then based on that, we can design a controller pi actually to generate some control signal, and then we can inject this control signal into the neurons of every layer. So in this way, actually we can tune the value of the neurons in every layer, and then in the forward propagation process, hopefully we can fix the possible error. We can fix the possible error before actually the forward propagation reach the final output. So if you just look at this top figure, look at this neural network, it may still look like feed-forward or open loop control problem, but actually it's not. Why? Because if you look at this dynamic system, if you look at this neural network from the dynamic system perspective, so here x0 is the input signal. Here x0 actually is not the input of the dynamic system. X0 is actually the initial condition of the ODE. If you just think about the neural network as the ODE. So the x0 input image is just an initial condition. And then what is the control signal? So what is the input signal of this dynamic system? So if you don't have any control, actually the input signal ut is just zero. It's just zero. But after we add the monitor E and after we add the controller pi, so actually at every time point, actually we can generate a control signal ut and then inject this control signal into the dynamic system. So that's why we say that this is actually a closed loop control system. It's not an open loop control. Actually, in this controller, actually there are two key mathematical blocks. The first one is actually the embedding block. The embedding block is used to actually detect the possible errors in every layer. And then another one is the controller block. The controller block actually generates the signal injected into the neuron. So the question is, how can we design the controller? So if you want to design the controller, and then normally we want to know what is the goal, right? So because we think about it from the dynamic system perspective, actually this problem is very similar to the classical trajectory optimization in the robot. So in the trajectory optimization of the robot, so normally we first plan for a trajectory for the robot. For instance, we want the robot to move from the starting point x0 to the final point xt. So the black line is a designed trajectory. But in practice, because the nonlinear dynamics of the robot and because the disturbance of the robot actually may not exactly follow the desired trajectory. The robot may walk further and further away from the designed trajectory, and finally it may just achieve a wrong destination, right? So in the control of the robot, so they can also add a closed loop control to enforce the actual trajectory get closer and closer to the correct trajectory, and then finally achieve the target final state. So this is the idea from the trajectory optimization. We want to borrow this idea to design the controller. But there's a key difference. The key difference is that in the deep neural network, we don't know in the inference, before the inference is done, actually we don't know the final point. Why? Because when we do the inference, actually we don't know what should be the correct label. Right? Because we don't know the correct label, so it's very hard to say how we should control iron, right? How we should control the trajectory and which point we should finally reach. So instead of enforcing the neural network to achieve a final point, actually we want to control the trajectory of the neural network to make sure that you get close to a good manifold. So what does it mean? So if you do the neural network training, if you train the neural network on the clean data set, we know that neural network can have very high predictive accuracy, right? So if you look at the trajectories from the clean data samples, and most of the samples actually, for most of the samples, the trajectory actually behave very well. So actually, if you connect all the trajectory from the clean data samples, actually we can construct a low-dimensional manifold. Okay, and then here the dashed red curve is a controlled trajectory of the neural network. So it may start from a perturbed image, and then in the inference stage, we want to control the feature and trajectory of the neural network to make sure that it gets closer and closer to the desired manifold of the clean data. Okay, so we want to use a low-dimensional manifold to describe the trajectory of the clean data. Okay, so there are many possible ways to to design this to design embedding function to reconstruct that manifold. So here I just show the key idea. So the key idea is as follows. So we have in every layer we have xt, which is a feature vector of that layer. As I said, it can also be a snapshot of the trajectory in the time domain. And then the trajectory can be of dimension n. Okay, but we can do a low dimensional projection to map it to a lower dimension r vt. And in this lower dimension, actually, we can capture some dominant component of the desired trajectory, right? And then we can do a reconstruction, project it back to the original d dimension to reconstruct the trajectory. So a very simple example could be a SVD, right? So if we have the clean trajectory from the training data set, we can have multiple feature vectors in every layer, right? And then we can do SVD to extract the dominant component, right? And then we can do a reconstruction, project it back to the original space. But we can also do it actually in a nonlinear way. SVD is just a linear dimensionality reduction, and we can also do it in another nonlinear way. For instance, using a nonlinear, for instance, autoencoder. Okay, now we look at the control process.
And can I ask a question?
Sure.
If I don't know if you actually do this, but that will take, if you have 10 layers, you have to do that. That's a lot of extra work, right?
Yes, but so in practice, actually, we can do a trade-off. We can do the embedding and control for every layer, but we can also do the embedding and control for only a small number of layers.
Okay, because I thought, okay, I mean, it's hard to safeguard 100%.
Right. It's very hard to safeguard 100% because if you do the embedding using the low dimensional subspace, actually we will lose some information.
Thank you. Okay,
so we describe this low dimensional embedding as a function E. So T is just an index for every layer. So in the inference stage, we have xt. Xt could be the possibly perturbed trajectory caused by the perturbed sample, right? So after we do the embedding, actually we can project the trajectory actually to the low dimensional manifold, and then we can measure the distance between the projected trajectory and also the original trajectory. So this is the reconstruction error. So if the error is very large, and then we say that, okay, this our trajectory is far away from the desired manifold, and then we should control the trajectory. So this actually could be used as a running loss in the control. So in the control in every layer, we can measure the distance between the actual trajectory and also the projected trajectory on the manifold, and then we can add a regularization to infer that the control signal is not extremely large. And then when we design the overall loss function for the whole control process, and then we can sum up the loss of every layer except the last one. So here we ignore the last one because the last layer actually is the output label. We don't know the output label in the inference stage. So after we form this control loss function, and then we can solve this control problem using, for instance, some open control solver such as the PMG solver. It's just an adjoint method to calculate the gradient and then to do the gradient descent.
Excuse me, can I ask
Yes.
a quick question here? Hi,
Sure.
This is Panos Tinis from Pacific Northwest National Lab. So can you go back to the previous slide?
Sure.
So I have, actually a couple of questions. First of all, why is the reconstruction on the manifold? What guarantees that?
Excuse me?
Why is the reconstruction, the capital E, why is it on the manifold?
So actually here, we design, actually this is you can regard this as a projection step. You can regard it as a projection step.
But you called reconstruction where you go back to Rn. So what guarantees that in Rn, this capital E, whatever you call it, embedding or something else, will be on the manifold? It may be elsewhere, right? I mean, it doesn't have to be on the manifold.
The reconstruction process actually is on the manifold, but the actual trajectory actually may not be on the manifold.
That I understand, but I don't understand why the reconstruction stays on the manifold. That is actually a process of how we design the embedding function, right? If we design the embedding function using, for instance, using autoencoder or using SVD. So for instance, if we look at that in the SVD, right? Yep. If you just think about it from SVD, right? So basically, we first have XT, and then using SVD, we have projection matrix to V, right? Right. And then we may have projection matrix, for instance, another projection matrix, let's say it's a projection matrix W. And then when we do reconstruction, we just need to multiply it by, for instance, W transpose. Okay, so this reconstruction is not a decoding step. You can see it as a linear decoding, right? So for instance, if you it's linear decoding. It's linear decoding.
Right.
So you still use a linear combination of VT.
For the linear case, yes. For the linear case, if you think about it from SVD, for instance, in the low-dimensional projection, if you say it's a matrix W, right? We multiply XT by matrix W, right? And then in the second stage reconstruction, we multiply it by W transpose. Okay, right. But in the nonlinear case, I don't know if you will stay on the manifold. But anyway, assuming that you stay there, what does the reconstruction error, when you add it in the loss function, what does it do? I mean, when you make it small, what do you get? So when we make it small, so normally we keep the, when we make it small, so normally we actually generate, we perturb the trajectory to make sure that we only, for instance, keep some dominant features in VT. Okay. So basically, you can also regard it as just like the control process is more like a filtering process, right? So if you look at the trajectory, if you look at the feature at every layer, and then it could be a combination of many basic features, and some of the features they could be very sensitive to the perturbation, and then they could destroy the accuracy. So we want to, in the control process, so basically this embedding process actually is similar to filtering out that kind of unwanted features. Okay, I don't want to disturb the flow of the talk. I'll ask you later. Thank you. Okay, and also you ask about how to construct, how to keep that on the manifold. Actually, in the machine learning community, there are some manifold learning approach, and actually the convolutional autoencoder is actually one of the popular methods to do that. Okay, thank you. Okay, so because in this self-healing process, so just like a human body, we don't, in a human body, actually when the human body do the self-healing, the human body does not need to know what type of virus or what type of bacteria attacking our human body, right? So similarly, for this self-healing neural network, we don't need to know what type of attack or perturbation we have in advance. So here, the first example shows that phenomenon. So we consider neural networks just trained in a standard way. So if the neural network is trained in a standard way, and then we can attack the network using different kind of perturbation, right? For instance, we can use a manifold attack, FGM attack, PGD attack, and a CW attack. So we can see that this neural network actually, under different kind of attacks, the first column actually shows that the accuracy decreased a lot. And then, but after we add this self-healing, this self-healing process, and then we can dramatically boost the accuracy. We can, for instance, we can increase the accuracy from 20% or 5% to about 80% under the manifold attack. And actually, it works for multiple types of attack. It's not just only work for manifold attack. It also works for FGSM, PGD, and the CW attack. Okay, and I just said that this process is a closed loop control. The control signal actually, when we design the control signal, actually we need to consider the overall loss of the whole system. So it's not just simply a filtering out process. So if you compare it with the reactive defense is just to filter out the undesired feature in the data sample. So it's exactly a filtering process. So if you compare it with the reactive defense, because this is a closed loop control, right? And then we do the filtering in every layer, and that filtering process also actually is coupled among different layers. So actually, we can achieve actually better performance than the reactive defense. So actually, so here the blue data actually show the extra accuracy improvement compared with the reactive defense. So how does it compare with the adversarial training? So we know that one technique to handle the adversarial attack is to include the adversarial attack in the training process. And but the limitation of the adversarial training is that once we specify the attack information, and the model normally works very well for that specific type of attack, but the model may not work very well for other type of attack. So for instance, for the FGSM training, so the training model works very well for the FGSM type attack, but it does not work very well for other type of attack, such as manifold attack, PGD attack, and a CW attack. So the blue curve, the black data shows actually the model performance trained by under the FGSM attack. However, if we further add the self-healing mechanism to the adversary trained neural network, we can see that it not only works very well for the FGSM, it also works very well for other type of attack. Okay, so this is because when we design the self-healing process, we don't require any prior information about the attack. Okay, so I have described the self-healing process to address the robustness issue in the inference stage. And now I'd like to talk about the responsible AI issue in the training stage. So in the training stage, actually, we need to care about the environmental impact and also the economic impact of the neural network training. So that's why we propose actually the Tensor-Compressed end-to-end training process. So firstly, why we need to care about the compressed training? That's because as actually the AI model becomes larger and larger, it actually consumes more and more computing power. So for instance, it has been reported that the computing time per DAG actually increased by almost 2 times every 3.5 months. So nowadays, for the big model, actually they have to be trained on the supercomputers. And 3 years ago, there was a very popular paper published by the University of Massachusetts MS. They have shown that training the large deep learning models, such as the transformers in the latent language processing, can produce a lot of carbon emissions. Actually, they compare the carbon emission with that caused by the flight, and also by the vehicles used in the United States. They find that actually the carbon emission actually is caused by the AI training. Actually, is very significant. For instance, training the transformer model, it can produce 5 times of carbon emissions compared with the carbon emission produced by one vehicle for 1 year, or for the whole life in the United States. So actually, this year I even saw a call for proposal from Meta because high energy costs in the data center. Of course, in the data center, the deep learning training is not the only source of consuming the electricity. There also are other type of tasks such as database management, right? But the key question is that because the big data and because the AI, the data center actually is consuming more and more electricity. And right now, Meta is even thinking about how to design the nuclear fusion to supply the power supply, to supply the electricity to the data center. Okay, so because the high hardware costs and also the high energy costs of the training large AI models, this motivates us to rethink the training process. So in the typical AI development, we first train large-scale models, for instance, on the HPC or on the supercomputer, and then we generate a very large model. But after we generate a very large model, in many cases, we find that actually the model has a lot of redundancy. And we can do compression, pruning, or logic distillation, and then to shrink the size of the model. And then we can deploy the model on some cheaper devices, for instance, for edge computing. So a key question is, can we skip the full science training on the expensive supercomputers, and then can we directly do the compressed training to generate the tiny model? And by doing so, perhaps we can significantly reduce the requirement of the memory and computer resource, and finally also reduce energy costs. So this is the main motivation. So what is the application of this methodology? So if you can really do the compressed training with limited hardware resource, actually it can open many new applications. For instance, if we do the training on the cloud, we may highly reduce hardware costs, right? If we can do the compressed training, we can even do a lot of on-device training. For instance, the pins has been used in many scientific applications, for instance, in the robotic control and also in the medical imaging. And in these applications, people care a lot about the computing on the edge device. But on the edge device, we have very limited energy and memory budget. But if we can do the compressed training, we can move the training actually directly to the edge device. And another possible application could be the federated learning, right? In the federated learning, the main challenge is the communication cost between the different nodes in the network. So if you can really do the compressed training, and then we can save a lot of communication bandwidth. Okay, so what is the key idea of the compressed training using the tensor representation? So firstly, look at the standard training process. In the standard training process, we want to train the model parameters such as the embedding table or weight matrix. So it is W. So here we just show a two-dimensional matrix in the machine learning model. Instead of thinking about the training process from the matrix perspective, we can think about it from the tensor perspective. For instance, we can partition the matrix into many blocks and then stack them together to a 3-dimensional data array, which is a tensor, or even a 4-dimensional or 5-dimensional tensor. And then if you look at them from the tensor perspective, we can do the compression, such as CP decomposition, packet decomposition, or tensor chain decomposition. They are just the higher order generalization of the SVD. So now instead of training the original model parameter W, we can train the low-rank factors in the tensor factorization. So we can change the variable. So instead of training W, we can train the theta in low-rank tensor representation. So in this way, actually, we can significantly reduce the number model parameters. For instance, for some very large model, we may reduce a model parameters by 1,000 times. So if you can reduce the model parameters by 1,000 times, and then a lot of things can be done on the single CPU on the edge device. So why the tensor representation could be a powerful option to do the training? So here I show one example. So this is the extremely simple example. We consider a matrix with about 1 million elements, and all the elements are 1. So we know that this matrix is definitely a rank 1 matrix, right? If it's a rank 1 matrix, and then we can do SVD, we only need 2 vectors to represent this matrix. So if you use SVD to represent this matrix, and then we need about 2,000 elements, right? So that's the best compression we can get from the matrix perspective. But actually, we can do further compression. Why? So if you look at the vectors in the SVD, actually there are still a lot of redundancy in the vectors, right? So instead of doing SVD, we can think about this compression process from the tensor perspective. So we can follow this matrix to a 20-dimensional tensor. So in every dimension, we have size of 2. Okay, so we still have 2 to the power 20 elements in this in the model parameters. But now, if you look at this tensor could be written as the outer product of 20 small vectors, and each vector only has 2 elements. So in this way, actually, we only need to use 40 elements to represent the original 1 million element matrix. So in this way, the reduction ratio could be 26,000 times. Okay, so this is an extreme example. So in the practical case, the model parameters cannot be rank 1, but the key idea is that if the model could be the model parameters could be well approximated by a low rank representation, and then we can still get a very high reduction ratio in the training process. So there have been a lot of work in this research direction, and most of the work focused on actually using the tensor compression to compress the already trained model. But more challenging is actually to do the training from scratch. And if you do the training from scratch, and then one challenge is actually how to determine the tensor rank. And most of the existing approaches fix the tensor rank. They assume a tensor rank in the training process, and then they optimize the low rank tensor factors. And in our work, actually, we want to do the rank adaptive training. We want to do the rank adaptive training because we don't want to do the combinatorial search of the tensor ranks. We want to do the training for only 1 run and then to get a tiny model. Okay, so now I will introduce the idea about the low rank tensor, the tensor rank determination, and also show why it is a difficult problem. So let's consider a tensor. So here I show a three-dimensional tensor for visualization, but in practice, it could be an n-dimensional. It could be a d-dimensional tensor. So it could be a d-dimensional tensor with, for instance, n to the power d elements. And for the d-dimensional tensor, we can represent it, for instance, using CP factorization. We can have, for instance, rank R. So basically, we have R rank 1 tensors. And each rank 1 tensor could be written as the outer product of n vectors. Okay, so definitely if we can know the correct R, we can have very highly accurate representation. But the problem is, what should be a proper value for R? Right? In practice, we may, if we just do a guess before the training, we may provide a very large R. If you provide a very large R, and then we may need to train a lot of model parameters, we waste a lot of hardware resource. And if you provide a very small R, and then the training process actually may generate a low accuracy model. Okay, this problem actually becomes more complicated in other tensor formats, such as Tucker and TensorTrain, because in that kind of format, R is not just scalar, R is a vector. So if we do the search, we need to do a search in high dimensional space. So exactly determining the tensor rank actually is NP hard. So the key idea is that we don't need to exactly know the exact number of the tensor rank. In the training process, we only need to know a proper number R. Okay, so this actually allows us to do the training
Bayesian perspective. So here is a high-level key idea. So we don't know what should be the exact tensor rank, but at the very beginning we can just provide an initial guess R prime. Okay. For instance, the exact rank might be 15, but our initial guess might be, for instance, 25 or 20, something like that, maybe far away from 15. But that doesn't matter. And when we set up the model, we can introduce some rank shrinking prior distribution. And then based on the data and the model structure, we can have a likelihood function. And then if we combine the likelihood function and prior distribution together, and then we can apply the Bayes rule to have a posterior estimation of the tensor factors. And then from the posterior estimation, we can decide the actual tensor rank R. Okay, so if you look at this whole process, actually, first we can initialize tensor rank R prime. The initial tensor rank R prime could be accurate, but it's mainly used to shrink the model size. And then with the Bayes rule, when we do the posterior estimation in the training, we can estimate a much better tensor rank and also the tensor factors. So this way, we can further get some model compression in the training process. But the main goal actually of the Bayesian rule actually to boost the training accuracy. Okay, so this is the Bayesian framework because a lot of audience here, you're very familiar with uncertainty quantification and machine learning. So I will skip the detail. So the key is that, so when we do the Bayesian, when we do the training from the Bayesian perspective, there are two key questions. The key question is, how should we choose the prior distribution to make sure that the model actually can automatically shrink in the training process? And another one is, if we want to do the training from the Bayesian perspective, and then how can we compute the posterior density efficiently? Because training the deep neural network, especially large deep neural network, is actually very expensive problem. So here I show the key idea of designing the prior for the CQ format, and other format can be handled similarly, such as Tucker and TensorFlow could be handled. Similarly. So here we use order three tensor as example. So here we use different color, green, blue, and red to show the factor matrices for every dimension. So at the very beginning, we may choose the wrong initial rank, for instance 3. Okay. But we can choose actually a prior distribution with a hyper prior p lambda. Okay. Lambda could have some, for instance, sparsity enhancement distribution, such as log uniform distribution or half Cauchy distribution. So we see that its density is very high, around 0, and decays very fast as the magnitude on lambda increase. And then we can use lambda as a variance parameter, and then using Gaussian distribution to generate the prior distribution for the tensor factor. Okay. In this way, for instance, if lambda is very small, and then the variance of the Gaussian distribution is very small, and then if you generate a sample using the Gaussian distribution, and then the whole column will have very small magnitude. So that whole column will be very close to 0. So in the training process, and then finally we decide the posterior density of lambda. So finally, if lambda had a very small value, and then the whole column actually will become very close to 0, and that column could be just removed in the training process. And then the model size can be further shrinked. So this is a graphical model of this tensor training, right? We have a hyperparameter lambda. It's equipped with a sparsity inducing prior distribution, and then we use lambda to generate the rank shrinking distribution for each tensor factors, right? And then we plug in the tensor factors to the model parameters, and then to construct the likelihood function in the forward propagation. And then we do the posterior estimation using Bayes rule.
And another challenge is how we do the training. If you consider the very large scale deep learning models, such as recommendation system, they have a lot of model parameters, and it's very difficult to do the Bayesian training in high dimension. So to solve that problem, actually, we consider this problem from the variational inference perspective. Specifically, we want to compute a density function Q to approximate the exact posterior density by minimizing the K-air divergence between Q and also between Q and the posterior density. Okay, so this is a key idea. And to save the computation cost, the key challenge is actually how to properly choose the density function Q. Okay, so here we want to reduce computation cost, so there could be a trade-off, right? We need to simplify density a little bit to save the computation cost. So here we just assume that Q actually is a product of some multiple density of different groups. For instance, every tensor factor could be put in one group, and the hyperparameter could be in another group, right? And then we can assume that we can simplify the posterior density over every tensor factor as the Gaussian distribution. So in that case, we only need the posterior mean value and the posterior variance for every model parameters, and we only double the model parameters in the Tensor model for the Bayesian training. And also, if you use a stochastic variational inference in the training, there's another numerical issue. So actually, the gradient will explode. That is because actually the stochastic gradient actually is inversely proportional to lambda. Okay, to solve that issue, actually we will further simplify the posterior density of lambda as a delta function, right? And then this will allow us to do the hybrid parameter update. In the gradient descent update, we can do an analytical update for the hyperparameter lambda, and then we can use a SGD to update the tensor factor. Okay, so by combining this kind of idea together, we can really train very large scale model using this Bayesian approach. So this table shows the performance of different models. We consider a very simple two-layer fully connected neural network to very large deep network with this is actually a deep learning recommendation system from Facebook. It has more than 4 billion model parameters. Okay, so using this kind of tensor-compressed training, so if you look at the accuracy basically is still at a similar level of the standard large-scale training. So for some of the model, we can get a slightly better accuracy. For some of the model, we can get slightly lower accuracy. But the main advantage is that we can compress the model a lot, and especially for large model. For instance, for the natural language processing model and for the deep learning recommendation system, model, they have very large scale weight matrix and a very large scale embedding table. They can get hundreds or even for instance 25,000 times of reduction in the training process. So this figure actually shows how the compression actually is obtained in the training process for the deep learning recommendation system. So for the deep learning recommendation system, the blue bar shows the original model parameter is 4.25 billion. And then when we use a tensorized representation with inaccurate initial rank, we can shrink the model size to about 2.4 million. Okay, so this step is about reduction is about 2,000 times. Okay, and then when we do the posterior density estimation, we can further shrink some of the tensor factors. We can actually shrink a lot of the columns in the tensor factors to 0. So this will further shrink the model size. So finally, we have a model size of about only 164K. So the overall reduction is about 26,000 times.
So if we can do this kind of compressed training, actually we can do a lot of things with a lot of training with very limited computing resources. Here is just one example. We do the training on the FPGA. FPGA means field programmable gate array. It's a very tiny embedding computing platform. Because we can compress the model parameters so much, actually we can put all of the model parameters in the on-chip memory. The on-chip memory actually computes much faster than the off-chip memory, right? And on the FPGA, we can also use some low precision representation to represent the model parameters. So here is the compression. For the full model, we consider the function M is the data set. For the full model, it requires 15 million bytes to represent the model. Okay, but if you use a rank adaptive tensor training, and then we can reduce the model parameter by 43 times. And on the hardware, if we further use some low precision representation, and then we can get another 7x reduction. So in total, we can get about 300 reduction of the model parameters on this tiny device. So because we can get 300 times reduction of the model parameters, actually we can train this model very easily on this tiny device. So if you compare with the training on the embedded CPU, we can improve actually the speed by 60 times. We can reduce the energy by about 120 times. So this is just a preliminary implementation. We get an accuracy drop. We get accuracy drop because low precision algorithm actually is not good enough for the tensor training. So recently we have improved the low precision training a little bit, and also we have pushed the training to large models such as transformers, right? This is the transformer model. For the transformer model, we can see that if we only use a full precision Tensor-Compressed training, we can reduce the model parameters by about 32 times. And then if we further use a low precision representation in the training, actually, finally, we can get about 250 times the reduction in the training process. And the accuracy loss actually is also very small. Because George Group actually has done a lot of work in pins. Actually, also we find that actually a lot of pins could be used for the edge device, for the decision making, and for the medical image processing. So we're also pursuing the training on pins on the edge device. So we applied as a demo, we applied the Tensor-Compressed training to pins to solve a Helmholtz equation. This is a very small neural network. It only has 3 FC layers. So because it's a very small network, so the reduction ratio is not that significant. It's only 13 times. But if you consider more complex neural network with more layers and with larger size, and then the compression ratio could be larger. So this concludes my presentation. So today I just want to share my experience about responsible AI. And besides accuracy, we really need to care a lot of the societal and technical impact of the AI in the data connection, training, and inference, and application stage. And in this talk, I mainly talk about the 2 stage. Firstly, I describe a self-healing neural network. In the inference stage, it can handle the attack and perturbation without knowing the information at once. And then motivated by the sustainability and the energy consumption of the large-scale deep learning training, I introduced a Tensor-Compressed training process. The key idea is to design a Bayesian model to automatically shrink the model size in the training, and it had already been applied to train very large-scale models, such as deep learning cognition system. Could also be used for many on-device training, such as transformer and pins. And that's all. Thank you.
Thank you very much, Zhang. This lots of good ideas here, and because we have a similar interest on our new center for DOE, where we approach the problem from the more like spiking neural networks, but it seems that you get really good factor of 100 or more in this. So the FPGA implementation is interesting. Jerome, do you have any questions on?
Yes, I mean, this
Go
is,
ahead.
I am
Yeah.
Jerome Darbon from Brown University. I am an associate professor at the Division of Applied Math. So I also program FPGAs for scientific computing and so on. But when you, what kind of FPGA did you use? Because MPSoC is from Xilinx. Is it
It's
really
from-
tiny?
Yeah, this is a very tiny FPGA from Xilinx.
So the low end from
Yeah, this is a very
the
low end
MPSoC.
FPGA. Yes.
Okay. And well, I got many
Yeah.
questions, but maybe I will send you an email later. Yes,
Sure,
this
sure.
is quite interesting.
Yeah, sure. And George just mentioned the spiking neural network. Spiking neural network is also a very good option for energy to improve the energy efficiency, and because you just use a path representation, right? You use a binary representation on the hardware, so it's highly energy efficient. But I believe that this kind of tensor-compressed training could also be applied to the spiking neural network to further reduce model size and to boost the computation and save the hardware cost.
Jenny, here on the since we are on this slide, you said a low precision. What does that mean? Like a number will be represented? It's like 16 bits or below?
Yes. Low precision means that when we do the training to represent the model parameters, we can use different number of binary bits to represent the model parameters. For instance, on the CPU and the GPU, maybe the default representation use for instance 64 bits, right?
Yeah.
And actually we can actually reduce the number of bits to 8 bits or 4 bits for many cases.
4 bits.
For some cases, for transformer, actually, at least for transformer, we seen that for many transformers, if you only use 4 bits, and then we can get very good accuracy.
Magic.
So we can use.
Sorry.
So we can use very low precision. That is because we use a tensor representation. For instance, if we use a tensor representation, for every dimension we have 4 bits, and then if we do the multiplication together, they together actually can capture the precision of, for instance, 32 bits or 64 bits, something like that.
But do you have theoretical results for these compression techniques? Because I know about that, and then you verify afterwards using validation as you write. But you have the theoretical result that.
You mean the tensor compression or for the?
No, for the quantization.
For the quantization. For the quantization, right now, no. Right now, we only have theoretical results for the CP tensor factorization. It's not for neural network. We do the tensor completion, and for the neural network, we are still investigating that.
You see that, Jen? That's what I'm afraid that with all these approximations we're making, and we compute things faster, we can always compute the wrong thing faster. In which case, we'll have a responsible AI again. So we're trying to save the energy, and then we'll get the wrong answer faster.
Yeah.
And then we are irresponsible. So there's a vicious cycle.
Exactly. So definitely, we still need more investigation on the circuit part, right? If we do
so that's why Jerome's question is what guarantees that we have is that we at the end we have actually responsible AI.
Right. And I guess finally we may also need to use some technique of the, for instance, from information theory, such as the coded computing, to how to do the error correction using this kind of low precision computation.
Yeah. But certainly the gains are big. So I think that's really promising. I think that's why I was interested in your work, and of course the self-healing is important, but this reducing the footprint, the carbon footprint that everybody wants to do that now, it's kind of important. And there was a paper by C-Sale of Neil Thompson. I don't know if you see that last year. They were talking about that. From MIT C-Sale, there was a paper on that. It was an IEEE. And it was in the popular press. I can send it to you.
Sure.
On that. Sure. We have more questions for Jen?
Can I ask a quick question?
Yes,
sure.
Father.
So very nice, nice work, both parts. So I see a common assumption under both pieces of work, that there is
Yes.
some kind of a low dimensional structure,
Yes.
and moreover that you can find it. So in the first case, it would be the manifold. In the second case, that there is this low rank representation.
Yes.
So I've seen also some papers for the tensors that are used in machine learning, that for the problems that they're applied to, they seem to have a lot of sparsity there, which you explore here. And also for the problems, that have to do with dynamical systems, in many cases, there are these low dimensional structures. However, there are a lot of problems where this low dimensional structure is still high dimensional enough.
Yes.
So it's just, a general comment. Have you tried to somehow break these approaches?
Very nice question. Actually, this is actually a very important question in this direction. So regarding self-healing, I think definitely using the embedding and using low-dimensional embedding is just one of the possible option, right? For instance, another possible option could be the sparsity pattern in the feature vector, right?
Right.
And even if we think bigger, self-healing does not need to be done using the closed loop control, right? We may even not need the embedding at all, right? For instance, if you just think about the self-healing of the neural system, right? It does not use any control; it just use the regeneration process.
Right.
Right. So there could be many possibilities. And that is for the self-healing part. And for the second part, so definitely for many of the models, they have the low rank structure. We can compress them a lot in the training process. But it's true that for many of the models, if you only use a low rank approximation, and then we may not get very good accuracy. One extension could be doing, for instance, low rank plus sparse approximation in the training process. So for instance, we can describe, for instance, the model parameters as a low rank component plus a sparse component, maybe in the tensor space. That could be one option.
Okay. Yeah, that's a longer discussion. I know there is another talk coming up, but thank you.
Thank you. Thank you for your questions.
Tucker, maybe we can go with the second talk now.
Oh, yeah, sure.
A little behind.
Thank you, Professor Zhang. Our second speaker is Jerome Darbon. Jerome is an associate professor at the Division of Applied Math at Brown University. His main research interests include high-dimensional optimization algorithm overcoming the curse of dimensionality arising from open control problems and Hamilton-Jacobi partial differential equations, and also its application to image processing, data science, and neural network architectures. So without further ado, Jerome, you may want to start the presentation.
Yeah, thank you very much for the nice introduction. So in this talk, I'm going to present a paper by several authors about designing robust scientific machine learning method for optimization. So the paper is available on arXiv, and this is the title and the list of authors that you have here. Okay. The motivation of that paper starts as follows. The authors considers models, essentially phenomenological models, that are used in many engineering fields. And these models are used to represent very complex phenomena. These models are generally accurate, and then they can allow for extrapolation. But the main drawback in using those phenomenological models is that they are generally computationally expensive to evaluate. So when you want to use these models to optimize for certain quantities involving these models, for instance, you want to optimize certain parameters, or you want to control the system, or you want to perform inference, then the bottleneck becomes to evaluate efficiently those phenomenological models. So one of the tools to overcome this computational issue is to use a surrogate for this model for which you have an efficient method. So the authors consider the scientific machine learning methods or neural network as the surrogate model, which allows for super fast evaluation. And if you have your fast surrogate model, you can use it in your favorite optimization methods or control problem or inference scheme. What the author emphasized in their introduction is that, at least for the paper they mentioned in that paper, that the proposed methodology performed the optimization on the surrogate model, but you do not have the certificate that the solution that you obtain using the surrogate is actually a good solution for the original problem. So it means that there may be, or there is, most of the time in literature, according to the authors, a discrepancy about optimizing the original model and optimizing using a surrogate model, where you do not check that the solution that you obtain using the surrogate model is actually a good one for the original problem. So they cite different, They cite different papers involving different engineering applications, such as water treatment or oil refinery issues, or material screening and process optimization, to highlight this difficulty. And what the author proposed in that paper is essentially a methodology partially supported by theory to address these issues. So how can we recombine the optimization using a surrogate model that arises from machine learning and neural networks to effectively optimize the original problem? I want to mention here that actually this point of view is very classical in standard optimization techniques, where, for instance, this, if you do gradient descent method, the surrogate that you are using for designing this approach is to do an affine approximation of the function at the point. Or if you want to use Newton-based method, then you are considering a quadratic approximation of the function at the point. So you use this surrogate model for the function to design the update, generally what you call a step in the optimization problem, and then you are left with proving the convergence. The convergence in standard and classical optimization methods is generally based on establishing estimates, a priori estimates, in continuous optimization, and in combinatorial methods, and in discrete optimization methods, essentially you are leveraging combinatorial properties. So what the author proposed here in a more general framework, when the surrogates are not given by mathematical concepts such as affine maps or quadratic maps, and then followed by classical arguments, is to say, okay, if I change my surrogate using a neural network, what kind of methodology I need to do to ensure that I can use my surrogate model using machine learning and still converge to a solution to an optimization problem. So this is what the authors do. And they proceed as follows. The way it's going to work in that paper is that they're going to, what's going on? Sorry, I apologize. They're going to consider optimization problems that involve several objectives, functions. The method that they are proposing works as follows at the high level point of view. They're going to sample the model to acquire data that is going to be used to train or create your scientific model, typically the creation of a neural network. This data is going to be used to identify the neural network using meta-learning optimization. Then, once they have the surrogate, they can use it to optimize it, and they're going to design a robustness metric what they call also the scientific machine learning-based optimization robustness theorem to certify, in some sense, that what they compute using this approach is actually a good candidate for solving the original problem that involves no surrogates. And then they're going to give some numerical results for some very standard multi-objective optimization problems, and they give specifically 3 test beds. Then I will give the summary of the paper, and I want to mention here that I keep the notation of the papers if you want to match what's going on in the presentation and the paper, and I will clarify the notation when needed. So, in order to see what the author is, my recommendation, if you read the paper, is to directly go to the numerical example to see what the setup is. The problem that they are considering is typically to minimize here a function that has 2 objectives, f1 and f2. And each of these functions depends on here 2 variables, x1 and x2. You have an explicit formula for them. And you have also some constraints on the variables x1 and x2. So what they propose to do is to create a surrogate model using neural network or deep neural network to have a model for f1, a model for f2, a model for G1, and a model for G2. So this is the first step that they're going to do. Instead of working here directly with f1, f2, G1, and G2, they're going to sample the problem in order to create this surrogate model and then put it in a multi-objective optimization software. So this is the figure that represents globally the approach of the paper. You are given your original model or your original system. You're going to design a sampling scheme to collect data and to extract some information from the system that you're going to feed to essentially a meta-learning, a meta-learning approach. Come on. A meta-learning approach to create a new specific neural network architecture, deep neural network surrogate that you're going to use to optimize. And if you do a good job, then here we see in red that the optimization gives you the Pareto font that you want. But in order to certify that you get the solution that is needed, you're going to test it using a robustness test that the author proposed to certify, in some sense, that the whole approach, the whole process tells you that you are actually computing a solution using for the original system. So the authors describe now the first steps, the data acquisition, that is essentially a sampling scheme, the deep neural network meta-learning search, then the optimization method, and more importantly, the robustness test. So to summarize what the authors propose, it's a method based on 4 points. The first one is to sample the original system of the model. In the paper, they call that the design of experiments. Then using the samples that you obtain, you put that into a meta-learning approach to obtain the deep neural network architecture that gives you the surrogate model. Then you use that surrogate model into an optimizer for multi-objective functions. And then you apply the robustness metric that the author proposed to certify in some sense that the surrogate that you use is faithful to the original model. So this is what the paper describes, and I'm going to give you some of the details about these 4 steps before going to the numerical experiments. So first, the authors need to sample the problem. The proposed approach for sampling the model is based on Latin hypercube sampling scheme, so NHS scheme. What is the idea of using the Latin hypercube sampling scheme? The idea is, maybe you can have a look here at the bottom of this figure, is to partition the range of the random variable that you want to sample into, let's say, a regular grid. Here we are working in 2D, and you partition that space. Now, for each cell, you compute the cumulative probability density function on each cell, so that if you select one cell, then using this probability, you can sample the random variable that lies in that cell. And now we are left about how we're going to choose the cell first that we want to sample. So at the beginning, you choose uniformly a cell. Let's say you select that one. Then you draw your sample in that cell. And then you're going to remove cells in the first column and the first line, and you are left with the other ones. And you repeat the process. You're going to select a cell that satisfies your new constraint. You get the cell, you sample it, and you remove again the cells in the same column and the same row. And you iterate that until there are no cells available. So this is a brief overview of what the authors chose to sample. It's called the NHS scheme. And the authors chose that one, citing one paper that for certain problem, it is faster than standard Monte Carlo methods. Now, once you have the samples, then you feed this data into a meta-learning approach to find a good deep neural network that will be the surrogate of your original problem. So the way the author does that is as follows. You collect the data, and you're going to use the data for training, validating, and testing, the usual setup for training a neural network. But they also consider deep neural network where the architecture and the meta parameters are not fixed. So they essentially considers 2 kinds of variables that you need to optimize to during this meta-learning approach. One set of variables include the kind of layer that you want to consider, the number of layers, the activation function, and the number of neurons. And they also include another set of parameters during this quest for searching the DNN. And those parameters, for instance, include the learning rate, decay, the momentum, the number of epochs, and so on and so on. So once the authors identify the parameters or meta parameters that they want to use to get the DNN that they want, they feed that into a method that is called hyperband, where the reference is given here. That is a meta-learning approach to get the DNN of interest given the data that you have and the meta parameters that you want to optimize. So they use this method to obtain the DNN that will be used as a surrogate. So that method gives all the hyperparameters. So it gives you the DNN that you want to train. Then they train it the usual way, and then they verify using standard learning approaches that the DNN that they get is a good model for a good surrogate for the model that they want. Okay. Once they have the DNN, then they're going to use it to perform the optimization that consists of optimizing a multi-objective function. So essentially what the authors are interested in is to compute Pareto fronts of this multi-objective optimization problem. There are many approaches in the literature to tackle this very difficult problem. The authors chose to use a particle swarm optimization approach to do this optimization. And in particular, they use a recent one published in the paper that is called CSPSO. The authors do not give much detail about this method. I read the papers. We can talk offline about that. But the key point here is that they are using these algorithms based on this paper to perform the optimization using the deep neural network that they obtain as the surrogate model. So now we are left with the last
Jerome,
step.
can I ask a question here?
Of course, of course.
So there is a meta-learning, which means that they're choosing a surrogate. So the surrogate is not fixed. Every iteration, they could change the surrogate during the optimization loop.
They didn't, but they could, I think, but they didn't.
Okay, so so all this meta-learning stuff can be done offline, just a usual thing. It's not inside the big loop where you optimize and also you find another more adaptive, more flexible surrogate, right?
And the paper was not clear what the loop is. I thought at first that they were doing that, but it's not so clear to me, I got to say. Personally, I think it should be a full loop, as you say.
Yeah. Yeah, we use hyperband. They give you flexibility, but it's really slow. We use actually hyperband a couple of years ago when we were starting meta-learning. Yeah.
Yeah, I see. Any other questions? Okay. So now this is the last part of the paper before the numerical experiments about how they can satisfy, in some sense, that the deep neural network that they get is good for doing the optimization. So here the notations are mixing big letters, big F, and small f. So the authors do not explain in the paper what those notations are, but you should understand them as follows. Big F here is a function that takes value in Rn. And every time you have a little f here, it's a real value function. So do not be confused. This is a notation f of xy for a vector, and little f of x is a notation for a real number. So what they say is, if you want to approximate a function whose range is in Rn, then you can do that for each of the entry of the output, and you want to get an approximation using a neural network that is called H here. So f is the function that you want to approximate. H is your prediction using a neural network. This is how they write it. H here, it's given by the neural network. And what they write here is a universal approximation theorem that you have existence of a neural network such that this quantity is small. So again, the delta, the notation here for delta is the neural network that you obtain after the meta-learning optimization, and they want to verify that the neural network that you obtain satisfies the neural network, the universal approximation theorem. So the goal is they're going to propose now a statistical test to verify that the universal approximation theorem is satisfied. So again, using the notation, they say h, f is the function that I want to approximate. H is the approximation that I get from the neural network. And they say we want to estimate this probability, and this probability should be somehow as high as possible. Well, here, W is what they call uncertainty associated to the model prediction. I didn't really understand what that means, but they're going to remove it right after that. They put some assumption about how the model that you want to approximate is, and some standard assumption about deviations between the model that you want to approximate and your neural network. Typically, they assume Gaussianity. And what they're going to obtain is an explicit formula for what the probability is on the discrepancy of the function that you want to approximate at some specific points and the neural network that you get. So this is somehow the measure that they create to measure the discrepancy between the model evaluated at some point and the neural network.
Excuse me, quick question.
Yes.
So, because when they write down the phi I,
yep.
Doesn't this assume that the components of the independent and the dependent variables are somehow independent from one another?
Well, this is one. That's a fair point. I asked myself the same question. In the paper, they say not correlated. I mean, I didn't really understand. This is what they think. For me, I think we need independence, but they didn't give the details, and I didn't go through the, I mean, I'm going to go through the math that they do, but I agree with you.
Okay, I don't understand the sentence also. They say successive acquisition of capital X and Y. Do they mean successive that you acquire Y after X, or do they mean component by component?
And I think what they meant is of the based on the LHS scheme.
I see.
I think.
Okay. All right. Okay. Thank
you.
But
I agree. I mean, to be on the safer side, here I would put independence.
Right.
And but again,
unless they think that because they use a Gaussian, if there is no correlation, then they're independent. Maybe. But it's a bit, yeah.
Yes. Yeah.
Okay.
Yeah.
Thank you.
Right. So we are left here with that quantity, and now the so you did that for one sample, and now you're going to do that for several samples. So it's like they call it several predictions by the model, and the number of samples you're going to get is denoted by NP. So this is where you have the independence kicking in, where you simply do the product of the guys that you had before. Then you take the logarithm, and now comes the part where they write, we differentiate the quantity above, phi, with respect to delta. And I remind you that delta corresponds to the operator defined by the DNN. So I'm not so sure what they mean by taking this derivative because delta is a function, so that guy should be a functional derivative. So I'm not so sure about the meaning of that guy with respect to differentiation. Nonetheless, it makes sense when you look at the result that they want, because they say, if I compute this quantity and I set it to 0, then this is the constraint that you obtain. So essentially, it says that when you evaluate your model, your original model F at some samples or points, and you look at the approximation that you get using your DNN, if you observe 0, then this is essentially a necessary condition for optimality. Again, that formula here looks very formal, but nonetheless, this is the idea that they have. And here, that quantity that you get, F minus H, is the quantity that you see in the universal approximation theorem. So they say essentially that if you satisfy the universal approximation theorem, then that guy is not 0, it's like epsilon. And this is exactly what they propose. They say, well, I'm going to approximate, to define my metric, to define my metric by looking at the discrepancy between the original model and the approximation using a neural network on the points. I'm going to sum that, and I'm going to test if it's less or equal epsilon. So this is the metric that they propose in the paper. So I insist, it simply consists of evaluating your original model at some points and your deep neural network at some points, and then you want that guy to be smaller than a prescribed threshold given by epsilon. Now, what they do next is to say, how are we going to set this number of experiments that we need to acquire? And another way to say it is, how many times do we need to sample the original models? And so here, what the authors suggest is to do a statistical test. So essentially, now they put a statistical method where z-score corresponds to the level of confidence that you want in your test, and E is a parameter that pops up here, that is the maximum that you allow between the difference of the average population that you have and the average sample population. So that parameter is obtained using a statistical test by following this methodology. So this is what the authors propose to do. So once you have all these ingredients, you put them together, and then you can evaluate the approach on some simple examples, and this is what the authors are doing. So first, they consider that function called the Bean and Cone function. It's a famous low-dimensional multi-objective problem to test Pareto optimizer. So that function is simple in the sense that f1 is a quadratic and x1 and x2 are separable. Similar for f2, and you have a quadratic constraint for x1 and x2, and another quadratic constraint, but non-convex, for g2. And then you have some box constraint about x1 and x2. So now the authors empirically verify the condition that they have for the LHS sampling scheme. So they want to verify that when they draw the sample X1 and X2, that the cross correlation is 0. So they implement the sampler, and then they report the numbers, and this quantity is not 0, but it's very close to 0, and they conclude that empirically, the scheme that they are proposing is working. Then, after the sampling, they feed that to Hyperband to get the to perform the meta-learning, and they get a different neural network. One neural network for the first objective function F1, one neural network for the second objective function F2, and again, another one for the first constraint and another one for the second constraint. So these are the results that they obtain after using Hyperband. Then they empirically show some results about the surrogate model that they obtain. So in black, they evaluate the original function F1 at different points. And in green, they show the results obtained by the surrogate model for the first function F1, the second objective function F2, and the two constraints. And they empirically conclude that the surrogate models that they obtain looks good in some sense. They also do some statistical tests that they call the parity charts, where essentially you have the tested data that you obtain using the neural network and the prediction and the original model, and then you want them to be on the diagonal. And again, they give you some of these plots to highlight that it seems that the method is producing good enough surrogate models. They also give you numbers about the mean square error and mean absolute error for the objective functions F1 and F2 using the surrogate model and the true one, and similarly to the constraints. And you get these numbers that are somehow close to 0. Now, this is, I believe, the most interesting plots of the paper, at least for the test number 1. I think it's better to look at the figure on the right. This is the figure that you want to, that you plot in, when you have two objective functions to get the Pareto front. So the Pareto front for this problem is given here in blue and black. In red and black. So in red, this is the Pareto front that was obtained using the optimization methods, and in black, so in this figure, they are superimposed. This is the Pareto front that you obtain using the original function. And in green, these are the other points that were used during the sampling to get the surrogate model of F1 and F2. So by this figure, the authors want to show that using the approach that they describe in the paper, they are able to get the Pareto front of the original problem by using the surrogate model based on deep neural networks. And on the left, they are plotting in red the variables X1 and X2 that you use to compute the Pareto front for original model, and in green, all the values of the variables X1 and X2 that are used in the surrogate model. But again, the main point of the authors is to show in this figure that visually, we are able to recover the Pareto front of the original problem using the surrogate models. So using the methodology that they proposed to set up the number of experiments in the theoretical part, they set the confidence to be 99%, and then they say that the number of experiments that you need for this example to achieve this level of confidence is 381. So they are sampling the original problem with that numbers, and this is what they need in order to get the method working. And they again give you some metrics, errors about the robustness test for the objective 1, objective 2, and the mean square absolute error. Then they go to a second function. So I'm not going to pronounce it because I don't want to butcher the name, but it's still a classical function that you use for Pareto front computations, where you still have two objective functions. So the first one is simple. It's simply the identity with respect to the first variable. And now the second objective functions depends on three variables, and you have this somehow complicated nonlinear term with a constraint that tells you that each variables need to live in the segment 0, 1. They redo exactly the same methodology. They test first that the sampling scheme that they are using satisfy the assumption that they want. And so you get these figures to show that the cross correlation that you empirically observe is very close to 0. Then they report the neural network DNN that they obtain for objective 1 and objective 2 using the meta-learning approach. Then again, they empirically show how the surrogate model performs compared to the real data. And these are the figures that you see, and it seems to do visually a good job. And similarly for the parity charts, and similarly for the mean square errors, where those numbers are somehow low. And again, we go to the interesting figures. Here, the Pareto front for F1 and F2 is given at the bottom. And, oops, sorry. What we see is, again, in red, it's the Pareto front that you computed using the surrogate, and in black, it is superimposed on the red in the Pareto front using the exact original models. So again, they show empirically that they are able to compute the Pareto front using the surrogate model, and it's very close to the Pareto front that you want to compute. So these are, again, the Pareto front that are computed, and they are in accordance with the Pareto front of the original problem. Again, they put the same setup for setting the number of experiments, and in that problem, well, instead of 381, they got 382. This is, again, using the methodology that they proposed in the paper. And again, they report some metric and mean absolute errors for the robust test for the objective function. And you get those numbers. And they conclude the paper with a third test that is, again, another classical optimization problem for multi-objective optimization. And the problem reads as follows, where you have highly nonlinear objective functions up to dimension 3, and then you have quadratic constraints, and again, a box. I'm going to go quick because they do the same methodology and report the same quantities. And these are the Pareto front that they were able to compute using, again, the surrogate model in red, and in black, the Pareto front using the analytical definition of the functions. So I did the best I can to grab the figures, but I cannot see much. But my understanding, again, is that the red and the black coincide on those figures. And again, similar, they use a similar test for setting the number of experiments. And again, it seems that they always end up around 393. So more or less for each experiment that they consider, the number of samples is more or less always the same. They do not explain why. And again, they give some metrics. So the summary of the paper is as follows. The authors proposed a robustness test based on statistic to guarantee that the result they obtain using surrogate functions defined by neural networks satisfy, using the statistical test, the universal approximation theorem. Then, given the methodology and this test, they combine it into meta-learning approaches and multi-objective solvers. And they report the numbers using this statistical test to set the number of experiments. I just want to highlight 3 points when I read that paper. I have many more, but I think those could be of interest. One point that is not addressed in the paper is about the dimension of the problem that you want to consider. So it seems to me, because you are partitioning space and you need to compute the cumulative properties on each cell in the NHS scheme, that you suffer from the curse of dimensionality. So if you increase dimension, it seems that you need to replace the LHS scheme by other sampling schemes that do not suffer or mitigate the curse of dimensionality. Also, instead of designing statistical test to check the robustness criteria, then it may be good to have an estimate about the number of samples you need to do in order to get to reduce on the error. And more importantly, I think it's beyond the scope of the paper, but more generally in science, it's how we should couple sampling of the model and the optimization method in order to have, I mean, in an informed or intelligent way. Because as of today, and especially in this paper, the sampling and the optimization techniques that you are using are essentially independent of each other. And then you couple them using the statistical test that they do, but they are not designed, they are not co-designed. So globally or philosophically, I think that would be an interesting question. Thank you.
Thank you, Jerome. I think Shuyang, you also, I don't know if he's still logged in, but he also
I'm here.
paper.
I'm here. Yes, I
have any additional comments? Yeah.
I have the same feeling as as Jerome mentioned, especially at the beginning, the paper started with this sampling strategy and they use hypercube. And if we go to high dimension, maybe you can do quasi monocolor. But eventually, if the dimension is really, really high, maybe we still need to go back to monocolor. Therefore, we need to find some way to bridge the sampling strategy and the remaining part. Because the Dardon hypercube has some very good property, right? It's more or less like more uniformly distributed points. That's why it has good property. But then when dimension is really high, we do need to consider really true random sampling strategy. Then we need a bridge to connecting the component and the remaining part.
Yes.
Jerome, in the third example, can you go to that? I couldn't tell what. Can you use your cursor to tell us where is the front, the Pareto front? Because there's lots of red there, and
I know.
It's a 3D.
It's a 3D representation.
Okay.
It's a surface.
Yeah, I didn't see the third axis. Yeah.
And essentially, again, it's very hard for me to see the
like
figure
a
at the
shell.
top.
It's like a shell.
Yes, but essentially, my understanding is that every time you see the red, then you also have the black, so they coincide. But it's a surface. It's a 2D surface in this 3D Euclidean space.
Your comment about coupling optimization and sampling, that's very important. Have you seen the work that Themis Sapsis presented in the past on active learning using the log of the ratio of the likelihood? Forgot exactly the metric, but it seems to be very good. We just had a paper accepted with DeepONet actually as a surrogate for air events. So he's using that to get a minimum number of samples with the distribution with heavy tails and so on. So I think there is some connection there. I can make that paper available, but
yes,
it was just accepted, so I don't know if it's out there yet. But so in other words, if you include uncertainty quantification, then you can use active learning and acquisition functions, basically following acquisition functions. But the logarithm that they're using seems to be working. The ratio, normalized ratio, and the logarithm of that seems to work really well. Any other comments for the paper? I find the paper actually interesting that they have this integrated formulation now. I think like what Xu Yang was saying, that if to scale it up, you may end up going back to Monte Carlo, which is fine. But
But my understanding that the paper wants to advocate that we need to complete the loop, right? You use the surrogate to optimize, and you need to make sure that you go back to the original problem. That wasn't the main message, and they propose methodologies to do that.
But the theorem is a theorem. They prove the theorem, or they just...
No, I mean, no, I did. That's why I did copy and paste of all the math that they had. I mean, it looks formal to me. But again, I mean,
but they don't have a proof, right? They cannot have a proof, right? Because then they depend
when they say it's a proof,
delta.
I think it's formal. They give you the idea, but I don't think it's rigorous.
Okay. Any other comments? Okay, but Jerome, thank you very much, Jerome. That was very useful. Maybe we can look into this. I think everybody is anxious now to go and have some candy, Halloween candy. So great.
Okay.
Thanks again. Yeah, Jerome.
Thanks,
you can close.
Yeah, this is it for this week's seminar. Everyone has a good weekend and good Halloween. Happy Halloween. See you guys.
Yes.
Bye.